Okay, this video lectures is for explaining some of the basics topic about a signal, because especially for those who for those who are in a third year student, I think, because some of you still not familiar with digital signal processing or biomedical signal processing. So of course, image is a two-dimensional signal, which is still I believe that you are not familiar with that. So that's why I try to provide some basic information regarding that from these video lectures, as well as I try to explain what is the convolutional operations, where actually it start from the one-dimensional signal, how actually from one-dimensional signals, the convolution of one-dimensional signal can be extended into two-dimensional convolution operation. Okay, the process is almost similar. So by having this video lecture, hopefully you can understand where actually the convolutional operation come from in convolutional neural network. Okay, so again, I think I believe that in your signal and system class, I believe that everyone take that subject. You are learning about analog signal. Okay, if you remember analog signal, okay, analog signal, let's say a sinusoidal signals. Okay, so it's a continuous signals. So normally the standard notation that you use to represent this signal is xt. Okay, it's a time domain. However, if you after sampling, okay, sampling is a process of converting the analog signal into digital signal or discrete signals, so it will become something like this. Okay, so now the signal itself is not continuous anymore. It's a discrete signal. Okay, it's a discrete number represent your signals, and normally in digital signals it represented through this type of form, which is called impulse response. Okay, you have a line and then a one big dot there represent the amplitude. So this is called impulse response that represent digital signal. So normally the standard notation for digital signals is xn, just to differentiate between the continuous time domain and discrete time domain. They use the word n there to represent a discrete time domain, which is happen in digital signal. So in other words, in order to represent digital signal, this is how it's look like. So same as this one. Okay, this is another sample, another signal which is not a sinusoidal signal. Okay, it's a one sample or one example of digital signal that that have been represented as impulse response, and it's easy to interpret in this way because you can see the structure of the signal through the impulse response. And then instead of impulse response, you can also represent the digital signal in a metric like this. Okay, it's a metric forms. Normally if you see some book, they use a arrow there at the bottoms, that's to show that this value, which is the amplitude value, is 1. The location is at time 0. Okay, because if you just without this arrow, then you don't know which one is origin or is a reference where the time is 0. So that's why they put arrow there at the bottom of 1 or at the bottom of any numbers around here to represent that is 0. So if I put the arrow here, then that's mean my signal, if I draw in this way, it should be something like this. This one should be 2, this one should be 1, and this one should be 3. And then my 0 is start there, and this is -1, this is 1. So that is how they represent the digital signal. And then from this one-dimensional digital signals, they have extended it into two-dimensional digital signal, which is the most practical example of two-dimensional signals, digital signals, is image. Okay, it's a digital image. However, most of the digital image textbook always represent two-dimensional signal or image, digital image, as in matrix form, okay, as compared to impulse representation. So why is that happen? Is because, let's say if I want, this is my two-dimensional digital signal which is in a matrix form. If I want to convert it into impulse representation, then it should look like this, which is very difficult to see, very difficult to interpret, instead of looking at this one, because this one you can see, okay, this is your pixel size 2 times 2, and then this value represent the intensity value or the color value, while in one-dimensional signal, this one represent the amplitude and this one is represent the index in the time domain. So that's why in image processing, this one is more preferable than this one in representing digital signal or digital image, because in matrix form is very easy to see. In form of two-dimensional signal is more easy to see as a matrix form as compared to impulse response. So that's why normally we use a matrix represent the image, but actually it's a two-dimensional signals. Okay, finish about the representation. So now we talk about the convolution process. Okay, the convolutional process. Okay, actually this slide note is from biomedical signal processing slide note. Okay, I just take a few example of convolutional operation happen in one-dimensional signal, so then you can familiar with it. I just discuss the example, so it will make you more easy to understand what is how actually we operate the convolutional process in one-dimensional signal. Again, as you can see over here, okay, that is the symbol. Okay, that is the symbol of represent the convolutional process. So convolutional process is quite a unique operation. Why is unique? Because as you can see, if you do convolution between your filter and your input signal, okay, in this case the input signal is X, the filter or the kernel here is a H. So if you convolve between these two, you will get the output YN. Let's say if you make it you change it in another way, means that you are convolve between XN and HN, you still get the YN. So meaning that doesn't matter where is actually your input is located in this operation, either this side or this side, and doesn't matter where you put your filter, either this side or this side, you still get the YN. Okay, means that if you do like this or if you do like this, you still get YN. Okay, so if you extend the operation seems to be like this. Again, the convolution is a process of a sum. It's similar to multiplication. It consists of a sum of product between your HN and your X, or in our AI class we replace our H here with W, so between the W and the X. Okay, so a little bit different between the multiplication, matrix multiplication and convolution, again because of this equation. Okay, I don't have to explain detail how actually to interpret this equation. Now take a look at the example over here, how actually to compute this operation, which is a convolution. Okay, again, this is my, for example, this is my filter and this is my input. To convert to find the YN, again YN here represent our net. Okay, a net matrix. Okay, so in other words, in this thing, Yeah, and then of course it's a matrix, one dimensional matrix which represent our okay. This is represent your the net there, a matrix of your net. If you relate with your AI class, this is net, and then this is your filter W, and this is your X there. Okay, so again, this is your W, and now this is your input of the signal. Okay, so in order to compute this expression, so what you do is actually, for this example, okay, they just draw the structure of the signal back. Okay, this is 1 1 1 1. Okay, just assume that the arrow is over here, means that this is this value is at the location of when the time is equal to 0. Same goes to the X there. This one is the value where when the time is equal to 0. So if you draw it, is look like something like this in impulse response. Then this equation, how to compute this equation is, if you are, even you don't understand this equation, is by first you need to flip. Okay, you need to flip your xn here. You can see that here, if you want to do the computation there, you need to flip. If you see the pictures over here, if you flip with respect to y-axis over here, then your xn become this entity, which is this one already going into that side. It seems to be a mirror. This one is a mirror of this side. Or flip, you are flip from left to right, or from right to left. You just flip that signal. So anything at the 0 is not changing. Anything's at the right side will going to the left side. You are doing a flipping process. Once you finish flip this equation, these signals, then you will do sliding there. Okay, you will slide. You will slide your you will slide the one that you flip. Okay, meaning that you can see that you overlap this signal and this signal. That is where is y0. To find the y0, you need to overlap between this and this one, and then you measure the sum of product. So from here you can see that if I overlap this signal and this signal, the one that multiply, the rest will multiply with 0, because for example this signal and this signal don't have their, it's because the couple of this signal is 0, while this one is your where is your signal of hn and xn is overlap. So if you are overlap between that one, then anything multiply with meanings that this one is belong to your x, but for h the value is 0. So anything multiply with 0, you get 0 here. This also because your xn, I'm sorry, your hn have a value, but your xn don't have a value. So anything multiply with 0 become 0. This one 0, and this one, the one which have exist non-zero value is at this position where your hn and your xn is have some number. So which is 1. So 1 times 1, so is 1. So now your y0 equal to 1. And then next stage, you need to find y when your n equal to 1. So at that time you need to translate this one. You can see that you need to translate the xn there. Okay, originally it at this side, and now you are translating it into this one. Okay, let me draw it again. Okay, so originally when x, y, n equal when y0 the value of y when n is equal to 0 is just you are see which part is overlapping in this value, then that make your value equal to 1. If more than one overlap, more than one position overlap, then you need to plus together because of this summation operation. Okay, but once you finish this one, in order for you to find the y value when the n is equal to 1, then you need to translate your or shift your flip xn here going into that direction. Okay, imagine that you have this one, then this one. Okay, for this case only one overlap. This one is not overlap, but if you shift into that direction, okay, just shift this one. Okay, if you shift that one, now this one is at this point, and the one at this point previously will go into this point. So now you have a 2-point overlap with your xn now is overlap at the 2 point between your xn and your hn. So 1 times 1 is 1, 1 times minus 1. Now because of the summation, then your y1 become 2 there. Okay, then you will repeat the same process, meaning that you must shift towards to positive side as well as towards to negative side to find your y0, y1, y2 and y3. Just process all things that make the output yn have some number. Okay, you don't have to process up until infinity because of course it is a common sense when you are going towards shifting or translating the xn towards infinity, then you will get the y infinity equal to 0. So that's why we only process the index over here where the value is exists. Okay, so if you finish up, then you can plot back your yn. So y0 is equal to 1 because of this one. Okay, y0 is equal to 1, y1 is equal to 2, y2 is equal to 2. So you can see that the last one is 1, 2, 2, 2, 1. So that is how you compute the output of the convolution process. Okay, so as you can see here, the translation operation or the shifted operation need to be done in order for you to compute the convolutional operation in one-dimensional. So that's why when we discuss about convolutional in C and N, but that one is a two-dimensional signal, then you have a process of translation from the upper left corner into right bottom corner. So the translation happen because that is the nature of convolutional operation. Okay, so of course in this case don't get confused because the operation that because in this example they are this example it's compute by y to find the yn is equal to your again, if you remember, hn convolve with your xn. Okay, and you can also compute in this way, xn convolve with your hn, you still get the same yn. So in this case, the one that have been flipped is your xn. Okay, the one that have been flipped is your xn. You need to flip, and then you do some translation to get your yn. Okay, but of course in our case where when we apply the convolutional neural network, we don't do that. We do this way, means that this one we fix, the xn we fix, the one we do translation and flip is this one. We flip first and then we do some translation or shifting to get the yn value. Okay, so doesn't matter because the original operation of convolutional, you can do either either you can flip the and shift the hn, or you can flip and shift the xn. But of course in AI, the one that need to be do that is your filter, which is your hn, not your input. Okay, because it a little bit messy if you shift the translate the, I'm sorry, you shift the x. So because x is the input, no need to do that, because you become more and more complicated. So it's more preferable to do shifting and flipping and shifting at the filter side. Okay, so that's how the nature of convolutional operation in one dimensional, means that you need to flip the signal, flip the filter. Okay, I just focus on the filter. We just fix the input x, we flip the filter, and then we do some translation at the filter. So anything which is overlap, then you need to count how many elements are overlap, because that will represent the summation of sum of product in convolutional operation process before you can generate this value. Okay, now the issue is how actually, what happened in two-dimensional convolutional operation, what is actually happened, how to relate this with two-dimensional convolutional operation. Yep, this one. Okay, again, this is how for one-dimensional signal, if you want to find your y here, then you need to convolve between your h and xn. Again, in we just focus on do this thing, meaning that you need to flip your hn. I just fix my x, but I flip this one and translate this one. Okay, or doing a shifting process here just to find my xn. So in our case over here, if this is my hn, so the flip version should, how the flip version look like? It should be the one at the 0 must not change there. Okay, because you flip there at 0, because that is the reference point to be flipped. So that's why anything which is the n equal to 0 is not changing. So now this one is the amplitude 2 there. Now this one become -1, and now this one might become 3 is at the n equal to -3. Okay, this is a flip version of this one. Once you flip, then you can translate. You must put this one and this one at the same axis. Then you need to do translation operation of this one on this same in the same axis at this point there. So when you want to find y0, then y0, okay, no translation. Okay, when we talk about y0, means that no translation at all. So let's draw the h, flip h at this point. So this is the first point, this is your second point, this one is third point. So the red signal there show your flip version of hn, which have been drawn in, which is drawn in the same axis as your xn. So now you can, as you can see over here, the one that overlap is only this one. So now the rest is not overlap. So if you talk about the summation process there, this one is plus with anything which is the product is equal to 0, then you only leave this one. So now your yn equal to 1. And then how about y when n equal to 1? Okay, so what happened? You are translating your flips version at that direction because it's +1. So now this one will become your 3, this one will become your 2, this one will become your 1. So you have two value there overlap. The rest is not overlap, so that's why the product of the rest is 0, while the product of this one we have non-zero value, while this one is 1, this one is 2 times 1 is 1, so it's mean 2 plus 1 because of the summation. Remember the summation make it become plus, so it become 3. So you will need to compute this one going to that way as well as that way. Then you just proceed the one that provide the non-negative zero value. Okay, not proceed going towards infinity, because of course if you going towards infinity to this side or this side, you will get the y equal to 0. So just proceed the one that have a non-zero value. Okay, that is one-dimensional convolution. So how about two-dimensional convolution? Again, those who take image processing class, I already explained this one. So again, I do in a two-dimensional signal or image, we don't represent in impulse response, we represent in matrix, because it's more easy to see or more easy to interpret as compared to this one if you talk about two-dimensional signal. So let's say I want to do a convolution between these 2 points. Okay, just don't worry about the notation, because this is the standard way in many textbook. If you talk about one-dimensional signal, when they talk about filter, they always use the notation H there. Input is X and then the output is Y. In image processing, the input image is called F, where your F should have index X and Y, represent this coordinate, and the filter here previously we represent as a H, now it become W. Previously in one dimensional this is X, now it become F. So previously when in one dimensional signal you call this as a Y, now it become G. Okay, so actually this process is similar, meaning that when you apply two-dimensional convolution, okay, what you need to do is that you can either flip this one, you need to flip and shift this one, or you need to flip and shift this one. But normally we will flip and shift this one, because this is the filter. Okay, we don't want to make a messy when we are flip and shift the input image, because input image just make it fixed like that. When you want to do a convolution, you need to you must modify this one. It's more easy because normally the size of the filter is very small as compared to the size of the image itself, input image. So that's why we need to do manipulate this one. So first you need to flip this one. Okay, flip. So how to flip the two-dimensional signal? It's a little bit different to flip this one as compared to one-dimensional, because one-dimensional, if you want to flip, you just make it the reference there is 0 there, because the reference, because this one is one-dimensional, so the reference to be flipped is at the origin, where the origin here is 0. So that's why you flip from the left to the right. Okay, from the left to the right. But for two-dimensional signal, the origin you have two component. Okay, where you need to consider the x-axis, which is represented by this one, and y-axis, which is represented by this one. So in two-dimensional signal, in order for you to flip this filter, you must flip 2 times. First you need to you must flip this one, meaning that let's say this is my value A, B, C, D. Okay, if I flip 1 time with respect to horizontal axis X here, then my signal will look like this. B here, A here, now D here, C is here, because the one that is not changing is at the center, same like this one. The one which is not changing is the one that is 0, because normally x0 y0 of the filter is this point. So that's why this one is not changing. Let's say I put here as a E there, so it's also E over here. Okay, one flip at the horizontal axis, now it become like this. Okay, now A is over here, B is over here, C is over here, D is over here, because you are flip. You flip in this way. You are flip in this way. Okay, but that is only one time flip, because it is two-dimensional. So then you need to do another flip with respect to horizontal vertical axis. You must flip in this way also. So that's why after you get this one, then you need to flip with vertical axis. Now it become something like this, which is this one is A, this one is C, this one is B, this one is D, and this one is still E. Okay, you flip two times. One time vertical, horizontal, another time is vertical. So that is can be, the terminology is similar to 1D, where 1D one time flip because it's because of 1D, but for 2D you need to do two flip. Then after that, once you have this version, then you need to, you know, put it on the same axis like this one. This is your filter, the green one, while the black one is your input. Then you implement a sum of product operation like this one. The one which is exists, you get the value. The one of course most of the time it's exists, the value is exist, then you need to, that is your G. Okay, that is where you get your G matrix there. Okay, so you know, of course, wait, so the output in the G matrix there, normally the size should be similar to this one. Is this one is 5 times 5, then this is also 5 times 5. Okay, so this operation is for this one. Okay, then you are to translating here. You translate your window into that point. Then that is one is for this one. Then you do the same to get this one, this one, this one, this one, and this one, this one, and this one. So the question is, what happened to this value there? Because you are not processing this value. Normally in image processing, we just set it into 0, because we cannot go outside this border, because that don't have any value there. So that's why you set it 0. But don't get confused, because later when I teach about the operation in CNN, this one is not 0, because we have a concept what we call as a padding. Okay, later we'll discuss about the padding. What is the padding? Padding is the process of, if you want to have a value which is non-zero at the pixel which is close to the border here, you need to do some padding at the input. So then you, by applying a padding operation before you apply the convolution, then you can get the matrix size of the input and the output is similar, because in this case you can see that the size is similar, but this one is 0. Is not a good way to represent the information, because you already set the border as the 0. It might be this point, we have some information is this point that we ignore by setting this point with 0. So that's why there's a process of what we call as a padding. So padding is an important process in CNN, where in image processing we don't discuss about that, because normally it's more beneficial to set this one as a 0 as compared to applying a padding. But in CNN or in AI, when we learn CNN, we must not ignore that things, meaning that we need to discuss about the padding process, so you don't have to worry about that. Okay, so now there's another question. When I talk about two-dimensional convolution at the image processing class or in CNN module before, I ignore the flipping process. You can see that once I get my W here, when I apply the convolution, I just apply directly. I just do a translation process or shifting process without flipping the filter first. So why is that operation have been skipped during the two-dimensional convolutional operation? So why we do that? I think of those who take image processing can answer that. That is because in general, if you talk about image, doesn't matter is it image or two-dimensional signal, normally the filter here, the filter coefficient of two-dimensional filter, okay, two-dimensional filter coefficient, doesn't matter 3 times 3 or 2 times 2 or 5 times 5, the value, the filter coefficient is symmetry. Okay, it's not similar to one-dimensional. One-dimensional, the filter is not symmetry, meaning that's why when you do flip operation, this one become like this one. But how about like, okay, this is one example of filter in image processing. They call it averaging filter. Okay, this is averaging filter. Okay, every element inside this filter is equal to 1. If you apply two flipping operation in this way, you still get 1. So that's why normally in two-dimensional signal, when you are applying the two-dimensional convolutional process, the flipping process is not, it was skipped. It has been skipped because of normally the nature of this filter, the coefficient is always in a symmetrical structure. So doesn't matter if you flip or not, you still get the same value. So that is why we skip the flipping operation in two-dimensional signal. So this is averaging. And then I think if you remember, if some of you remember that, okay, this one is should be 1/9. Okay, 1/9. It's not 1/1. It's a 1/9. So there's another filter called Gaussian filter. Gaussian filter is something like this: 1 4 2 2 2 2 1 1. So you can see that it's a symmetrical structures. So it doesn't matter you flip or not, you still get the same value. So that's why we skip the flipping process. We just implement the translational process or the shifting of the filter to the entire input image. Okay, again remember from the left upper corner into right bottom corner. So you need to do that. Okay, so that is the historical behind two-dimensional operation, where actually it have been implemented in signal processing, image processing, as well as deep learning, where when they apply at the deep learning, they call it as a convolutional neural network. Okay, because they are doing the convolutional operation, replacing the metric multiplication in order to reduce number of connection between one layer to another layer, because you are handling huge number of hidden layer. That's why we need to reduce the connection, so it will make the architectures can be easily compute by your existing computer because it's not so heavy.